In this video, we look further at the serial adder to see how do we design it in a different way, and then we consider the universal register. We have taken slide in the previous video how to construct a serial adder using a D flip-flop, and we understand this thoroughly. In this example, we will take a different way of implementing a serial adder by using a JK flip-flop. Therefore, we can start doing this by writing down the state table for a serial adder. The state table will contain one flip-flop which has a present state Q and next state Q, and this flip-flop will hold the carry as we have done earlier. So this is connected with the carry output of the full adder in the previous method. Now, to construct the state table, we write down on the left-hand side the present state Q together with the inputs, which have 8 different combinations ranging from 0, 0, 0 to 1, 1, 1. And on the right-hand side, we write down the next state Q and the output S. Of course, a Q will be the most significant because it represents the carry, and S, the sum, will be the least significant. And for this, the state table will be as follows. Simply, this will be the carry output of the combinational circuit that we studied earlier. Therefore, for 0, 0, 0, sum will be 0 and carry will be 0. For 0, 0, 1 or 0, 1, 0, sum will be 1 and the carry will be 0. And for the next one, 0, 1, 1, which is we have 2 ones, the sum is 0 and carry is 1. And for the next one, we have 1, 1, so sum is 1 and carry is 0. And for the next 2 cases, we have 2 ones, so the sum is 0 and carry is 1. And for the last case of 1, 1, 1, we have 3 ones, sum is 1 and carry is 1. Now, in order to complete the design, we need to derive the inputs of the flip-flop, which are the J input and the K input, assuming that we will use a JK flip-flop because it's a little bit more difficult than the D flip-flop, which we have taken earlier. To derive J and K, we look at the present Q and the next Q as follows. The first 3 rows, Q was 0 and it remains 0. Therefore, J must be 0 and K can be don't care. We have taken this earlier in the previous chapter. And the next case, Q was 0 and it changes to 1. Therefore, J must be 1 and K is don't care. And the next case, Q changes from 1 to 0. Therefore, K must be 1 and J don't care. And the last 3 cases, Q was 1 and remained 1. So J don't care and Q is equal to 0. Now, from this table here, we can, if we want, construct a Carnot map for J and another Carnot map for K as function of Q, X, and Y. And we find out that JQ equals X and Y, and KQ equals X prime, Y prime, or X or Y prime. And the sum S is the very famous exclusive OR function, which means S equals X exclusive or Y exclusive or Q. Having done this, actually, it is now straightforward to draw because we start with drawing a JK flip-flop here. And this is the clear input, which we again discussed earlier. And we write down here the shift registers A and B as we have taken earlier exactly. So this will be X and this will be Y. And then for the shift registers, we have shift control and the clock coming to both of them, and shift control and the clock coming to the clock of the JK flip-flop. Now, the sum is generated as the exclusive OR of X and Y and the Q, as we have just derived. This is output of the flip-flop Q here, and JK and K, JQ and KQ are implemented by following these equations up here where we need one AND gate for J to AND X and Y. This is X and this is Y. And we need one NOR gate for the KQ, which is X or Y prime. So we have here X and Y, and this is X or Y prime. And that completes the second design for the serial adder. Now we move on at a universal shift register. A universal shift register, actually, it is a register that can be used in number of cases, as we will describe in this diagram here. Let us look at the register. Now, we consider a 4-bit shift register, so it has 4 flip-flops, A0, A1, A2, and A3, and these can be the parallel outputs of the shift register. And each flip-flop will have a D input and a clock input, and all the clock inputs are connected to one common clock, which is always the case. And also, all the flip-flops are connected with one common clear input, as we can see here, and this is active low, which means when a clear is 0, the register will be cleared. Sometimes we call it clear bar if we want. Now the register works as follows. In order to control the operation of the register, which has 4 different functions, the first one is no change at the clock pulse. Second function is shift right at the clock pulse, and then shift left at the clock pulse, and then parallel load at the clock pulse. To do that, for every flip-flop, we need a 4-to-1 multiplexer. 4-to-1 multiplexer will have 4 inputs, and then it will have 1 output. It operates as follows. Now, for the 4-to-1 multiplexer, we need 2 selection lines, which we call S1 and S0, connected to 0 and 1 inputs of the multiplexer respectively. Now let us look what will happen when S1 is 0 is 0, 0. Each multiplexer will pass the 0 input to its output. Therefore, this multiplexer, the 0 input comes from A0, so A0 will be here, and the next multiplexer, A1, will be here, and the next one, A2, will be here, and then A3 will be here. And at the clock pulse, each D flip-flop will load its input at the D, which is same as the output. Therefore, we say when S1 is 0, 0, 0, there will be no change in the register. Now, on the other hand, let us assume that S1 is 0 and S0 is 1. So we expect each multiplexer to pass its 1 input to its output. So we connect the multiplexer's inputs as follows. The 1 input for this multiplexer comes from A1. So this is A1. And the 1 input here comes from A2, and this comes from A3, and this comes from serial input for shift right. So the output of the multiplexers will be, this will be A1, and this will be A2, and this is A3, and this is serial input for shift right. Again, at the clock pulse, A1 will be loaded here, and A2 will be loaded here, A3 will be loaded here, and a new input will be loaded here. So as if we have shifted the bits from right to left. We call it shift right. Let us consider the third case, which is S1 is 1 and S2 is 0. Therefore, we erase this. We write 1 here and 0 here, and each multiplexer will select the input at its 2 input, the second input, it will come to the output. Now let us look at the multiplexers. What is the input at 2? The first multiplexer, it will be serial input for shift left. Therefore, this will be serial input will appear here. And the second multiplexer, it will have a note appearing here, because we can see that this is connected with a note here. And the third multiplexer, A1 will be here, and then A2 will be here. Now, at the clock pulse, again, each D flip-flop will load its input to appear at the output. The outputs will be as follows. This will be the serial input for shift left, and this will be A0, and this will be A1, and this will be A2. So as if we have shifted everything from left to right. We call it shift left. Finally, the last operation to this register is the parallel load, and this happens when S1, S0 is 1, 1. Therefore, when these are 1 and 1, input 3 of each multiplexer will be passed to its output. Now, at input 3, we connect I0 to the first multiplexer, and then I1 to the second multiplexer, and I2 and I3, and we call these parallel inputs. Therefore, with these selection values, we will find here I0, the input of the first flip-flop, and then I1, the input to the next flip-flop, and then I2, and then I3 at the D of the last flip-flop. Again, at the clock pulse, I0 will be loaded here, I1 will be loaded here, I2 will be loaded here, I3 will be here, and therefore we can say that the parallel inputs appear at the outputs of the register at the clock pulse. This summarizes in detail how does this multiplexer operate, and if you want to buy multiplexer from the market as an integrated circuit, this is closer to the register that you will buy. Now, this shift register, which operates as shift register operator, is very, very popular as a matter of fact, and it is available off the shelf in different forms of integrated circuits, and we only need to learn how does it function. Usually, we draw it as a block diagram, so all of this comes into block diagram, a circuit like this, which has the following. It has clock and clear, as we have explained here, and it has two selection lines, S1 and S0, will control the operation, and we call this mode control, because depending upon the values of S1 and S0, it will determine how will the register function. And then it has one bit for the shift right. We call it most significant bit in, because this bit, it enters from the most significant bit here, and on the contrary, we have another input, we call it least significant bit in, because this bit comes to this place here. And then we have 4 parallel inputs, I0, I1, I2, I3, and 4 parallel outputs. And this completely describes the implementation and the usage of this type of registers.